This is an example not from the textbook about rotational kinetic energy. And talks about two identical wheels moving on a horizontal surface, and the center of mass of each has the same linear speed, and later we're given that speed is 6.0 meters per second. And however, one wheel is rolling and also going at that speed, while the other is just sliding on a frictionless surface without rolling. And then each one encounters an inclined plane, and one continues to roll up the plane while the other one that wasn't rolling continues to slide up the plane. And eventually both of them come to a halt because the gravitational force slows them down. We know the mass of each wheel. We don't know the radius, which is a little concerning. Hopefully that's going to cancel out. And we want to know, first of all, what is the total kinetic energy of each wheel, and then how much each one's going to go up the inclined plane. All right, so the fact that this has kinetic energy in it tells us right away that this is an energy problem, and we should go to our work and energy problem solving strategies. But even if we hadn't had that and we just been asked to determine the maximum height, we might already think that we have kinetic energy going into potential energy and go to our energy problem solving sheet. So let's do just the analysis for part A and see if you can even finish the calculation, because part A is pretty straightforward. All right, so I drew my two cases, the sliding and the rolling. Here this one's rolling. It has some omega that we don't know, and it has some I also. Well, we know that's a half mr squared for a disk, and this is radius r. Okay, so we knew more than I'd originally put. Our goal is the total kinetic energy, and we remember that kinetic energy now is our translational kinetic energy, or kinetic energy from the center of mass moving along in a line, plus the rotational kinetic energy, the kinetic energy we have from spinning. And we know equation for both of those, a half mv squared plus a half I omega squared. And the sliding case is a really easy place to start because it's not spinning, so we don't have the half I omega squared. We just have this a half mv squared. So let's do that. Well, that's pretty straightforward. We just plug in the numbers and we get 36. The units are joules, and if we do them carefully, we see that we get kilograms meters squared per second squared, which is kilograms meters per second squared times meters, which is newtons times meters, which is in fact a joule. Great. So then we move on to our rolling case. All right, here we have the kinetic energy in the rolling case equals what we had before, a half mv squared, that same 36 joules since the mass and the velocity are the same. But then we add on this rolling energy, right? So this has more total kinetic energy than this one, and it's a half I omega squared. All right, so then a half I omega squared is the thing we need to find, and we don't know omega and we don't know I. We don't know either of them because we don't know r for one thing. We know for a disk, I is a half times the mass times the radius squared. We do know the mass, 2.0 kilograms. We don't know the radius, so I'm going to proceed and hope that the radius cancels out. So there we have that a half mr squared. And then omega, remember when something's rolling, its tangential velocity is the same as the velocity to the center of the mass. And that velocity is the radius times omega. So v equals r omega. And if we want to know omega, the angular velocity is just the velocity of the center of mass divided by the radius, which is the tangential velocity divided by the radius. So I plug that in here and it gets squared, and is looking good for the canceling of the radius. All right, so here we can see that if I just do this out, I do all my algebra, this turns into a fourth, this is r squared, this is a v squared now, and an r squared in the denominator, the r squareds cancel. Then I am left with this, which is interesting. It's a quarter of mv squared, so half, in this case, half of the kinetic energy is here. We have half as much rotational kinetic energy as we have translational kinetic energy. So we have 18 joules in rotational, 36 in translational, 54 joules total, right? In the rolling case, we have the translational plus the rotational, that should be an 18, is 54 joules. Great, so now we're done with part A, the total kinetic energy of each wheel. We need to determine the max height of each wheel as it moves up the incline. So here, this was just a pretty straightforward calculating the kinetic energy. Now we want to apply that in a new way where we're using rotational kinetic energy in a work and energy problem. So here's where you really want to go to your work and energy problem solving strategies for part B. All right, so go ahead and see if you can do that analysis and planning. I'm just going to copy these two over into our knowns and make us some space for part B. All right, so not only did I copy over the kinetic energies here, but I did a little more drawing and analysis. I figured, oh, now there's a start time and an end time. And the start time is when we're rolling along the flat part, and then the end time is up at the apex when we've rolled up to whatever the final height is here and have velocity 0. Similarly, oh, this one was a sliding one. We've slid up to the final height here where velocity is 0. And here we're rolling along and we roll up to a different final height where velocity is 0. Right? And my plan here is actually conservation of mechanical energy, because what's happening is if I tell myself in the energy story, down here, whether I'm rolling or sliding, I have some kinetic energy, and that kinetic energy gets transformed into potential energy, gravitational potential energy, as the ball rolls up or the disc rolls up the hill. And if I look at my energy problem solving strategies, I've identified the pictures. If I think about the forces that are acting here, friction is negligible in both cases. This one because it's rolling, this one because it's frictionless. And so that means all the forces that do work are conservative, and I can use conservation of mechanical energy. So the initial mechanical energy equals the final mechanical energy. All right, go ahead and see if you can finish the execution here. All right, here we go. And my initial energy, mechanical energy, is a kinetic energy plus the potential energy. That equals my final kinetic energy plus my final potential energy. Now here we have a lot of different ways of kinetic and potential energy to consider, right? Potential could be gravitational potential and spring potential now. Kinetic could be rotational kinetic and translational kinetic. The nice thing is we've already figured out our initial kinetic energy, so we don't even have to think about what that is. And we know our initial potential energy is 0. First of all, there's no springs involved, so we don't even have to think about spring potential energy. It's just our regular old gravitational potential. It's 0 at the start, because we start at height equals 0 before we roll up the hill, and then we end with some final gravitational potential energy. So what we see is what I was saying in the story. We start with kinetic energy that's transformed into potential energy. Now potential energy, the formula for it is mgh. So mgh at the end equals the kinetic energy at the beginning. We can do some algebra, solve that for the height. And we know the kinetic energy, and we also know mg, the mass of the object, and gravity. We plug that all in, and we get 1.8 meters. It's good to be a little careful with the units here. A joule is actually a newton times a meter, and all this at the bottom is a kilogram meter per second squared in newton. So this units cancels with the newtons, leaving us just the meters as we expect. All right, so I don't have a very good expectation for this, how high it would go. 1.8 meters seems pretty reasonable. But what I know is now that I did the sliding, the rolling should go higher because of the fact that it's rolling. It has more kinetic energy because it has both translational and rotational. And we see that in the number. It has more kinetic energy, 54 joules. So I expect it to go higher. But what's kind of nice, and what's one of the benefits of leaving the variables in until the very end, is that this formula still works. Here, we just have a different kinetic energy. So we really just plug new numbers into this formula to get the rolling case. I plug those numbers in here, and I get that the rolling one goes up 2.8 meters. So this is what we would expect. If they're both moving with the same center mass velocity, but this one's rolling, it just has more kinetic energy, and that means that it would roll higher up because it would want to end then with more potential energy. Similarly, we could imagine that instead of rolling up a hill, these were rolling into a spring and compressing it, right? So instead of going into gravitational potential energy, they could be going into spring potential energy. And then we would expect this one to compress the spring further because it has more kinetic energy at the start, so it should end storing more potential energy in the spring, or here in this case, storing more potential energy by going higher up the hill. Right, and it's kind of cool because we didn't need to know anything about the incline of the hill. We didn't even need to know the radius of the hoop, and we were still able to figure out how high it would roll up. All right, and now we're done with this example.